Hi everyone, in this video we're going to continue with the second part of our exercise. If you remember, in the first part of this exercise we had an example of individuals with diabetes and non-diabetes, and we wanted to draw a decision boundary to classify between diabetic versus non-diabetic individuals based on their body mass index and history of diabetes. So now, instead of following this parametric approach in which we draw a decision boundary, we are going to follow a non-parametric approach, and we are going to see how we can make a decision only by using the data samples. So essentially, we do not assume any structure about the data space. We just let our training samples speak for themselves. And this is the foundation of the k nearest neighbor algorithm that we're going to see in the later parts of this class. So the third part of this exercise asks us to compute the Euclidean distance, which is also referred to as the L2 norm, between sample X4 and samples X1, X2, and X3. And let me remind you that we had actually given all of these four samples. We know that sample X1 equals to 5, 1, sample X2 equals to 5, 2, sample X3 equals to 33, and sample X4 equals to 10, 1. And I assume in all these that each sample is a column vector. Therefore, that's why we have this conjugate sign here. So if we were to calculate the Euclidean distance between X1 and X4, by definition of the Euclidean distance, this would be the square root of the difference of each of the dimensions between the two samples. So it would be 5 minus 10 raised to the power of 2 plus 1 minus 1 raised to the power of 2. And this would be 5. Similarly, the distance between X2 and X4 would be the square root 5 minus 10 raised to the power of 2 and plus 2 minus 1 raised to the power of 2. And this would give us square root of 26. Finally, the distance between X1, X3, and X4 would be the square root of 30 minus 10 raised to the power of 2 and 3 minus 1 raised to the power of 2. So it would be the difference between these elements here and these elements here. And this equals to square root of 404. So then question 3b asks us which sample is closest to X4 based on its Euclidean distance. We see that the smallest Euclidean distance of all three is d X1, X4, the distance between samples X1 and X4. Therefore, X4 is closest to X1. Now, if we were to classify X4 based on the class of its closest sample, according to the Euclidean distance, the next question asks whether X4 would be diabetic or non-diabetic. So we remember that sample X1, we were given that sample X1 is non-diabetic. So we know that X1 is non-diabetic. Therefore, X4 is non-diabetic. And this is the premise behind the one nearest neighbor. Basically, if we have a test sample, we find its nearest neighbor and we assign to our test sample the label of its nearest neighbor. Now let's go to the next question, which asks exactly the same thing, but instead of us using the Euclidean distance, we use the cosine similarity distance. And this question has been designed to show you that actually the distance is one important hyperparameter of the k-nearest neighbor classifier. So depending on which distance we use, sometimes we can get different results. The choice of distance is also very much dependent on the data. So if we have data that might be representative more of a spherical surface, and we might be interested in the relative angle between this data, we might choose a cosine similarity distance. Versus if we have data that are more aligned with the grid, then we might choose a Euclidean distance. So let's go ahead and see how this will play out for the distance of cosine similarity. So the first question asks to compute the cosine similarity between samples x1 and sample x4 and samples x1, x2, and x3. So we start with the cosine similarity between x1 and x4. And by definition of the cosine similarity, we just substitute the dimensions of x1 and x4 in this formula here. So this would be 5 times 10 plus 1 times 1. Square root of 5 raised to the power of 2 plus 1 raised to the power of 2 multiplied by 10 raised to the power of 2 plus 1 raised to the power of 2. And all this would be 0.99. Therefore, the angle between samples x1 and x4, if we were to see from the trigonometric table, it would be around 44 degrees. Similarly, if we were to compute the cosine similarity between samples x2 and x4, we would have found that this is around 0.96. Therefore, the angle between samples x2 and x4 is approximately 88 degrees. Finally, for calculating the cosine similarity between sample x3 and x4, we can substitute the numbers into the same formula, and we will find that the cosine similarity between x3 and x4 is actually equal to 1. Therefore, their corresponding angle is equal to 0. And actually, it makes sense because if we go back to our 2D plot, we see here samples x3 and sample x4. Let me plot sample x4 here, 10 and 1. So sample x4 is here. And we actually see that if we were to draw a line between those two samples and the beginning, the origin of the axis, all these would be along the same line. That's why the relative angle between x3 and x4 is equal to 0. Therefore, these samples are collinear. So next question for B. asks which sample is closest to x4 based on the cosine distance. We see that samples x3 and x4 have a relative angle of 0. Therefore, sample x3 is closest to sample x4. And finally, 4C asks us to classify x4 based on the class of its closest sample according to the cosine distance. x3 belonged to the diabetic class, therefore x4 belongs to the diabetic class. So we see that according to the Euclidean distance, x4 was non-diabetic, but according to the cosine similarity, x4 is diabetic, which goes to show that the distance that we use to run the k-nearest neighbor with matters. So this is a hyperparameter that we have to control in our experiments and empirically see what is the best distance. So with that, thank you very much, and I'll see you in the next video.